Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Today we've got another installment of our CIDR series, and I'm really happy to say that I'm joined today by Wang, who will be talking about his paper, Developers' Responsibility or Databases' Responsibility, Rethinking Concurrency Control in Databases. Yang is an assistant professor at The Ohio State University, and he's currently on sabbatical at Meta. His research interests are distributed systems, in particular fault tolerance, scalability, and performance optimizations. And obviously, he is interested in databases as well, hence the paper we are going to be talking about today. So, Yang, thank you very much for joining us on the show.
Thank you for organizing this. I'm very happy to have this opportunity and have the chance to share my research with others.
Fantastic. Well, it's our pleasure to have you. So let's jump straight in then. So can you maybe tell us a little bit about your background, about yourself, and how you became interested in researching distributed systems and databases?
Okay. So I got my bachelor's degree in computer science from Tsinghua University in China, and also master degrees from there. Then I joined the University of Texas at Austin for my PhD degree under the advising of Dr. Mike Darling and Lorenzo Alvisi. Then after I graduated, I joined the Ohio State University as an assistant professor. Okay. Regarding why I'm interested in distributed systems and databases, I think usually that's a hard question because sometimes you just cannot explain your interest, right? So it's just you're interested in something, then yeah, you're interested. Okay. I would like to say that I like those things because. So first, they involve challenging problems, right? If you look at the concurrency control, if you look at distributed protocols, some of them are probably among the most intellectual challenging problems, in my opinion. And also, databases and distributed systems serve as the foundations of today's IT infrastructure in both big IT companies and even those university infrastructure and something like that. Okay, so they are challenging and important. I think those are the major reasons why I chose to pursue research in these directions.
Fantastic. Yeah, I just echo that sentiment. Like they're the sort of things that attracted me to these areas as well. I mean, like you said, there's so many interesting problems in this space, and there's enough interesting stuff there to keep you occupied for a lifetime, right? So right. Definitely agree with you on that one. Cool. So let's talk about the paper then. So developer's responsibility or the database's responsibility, rethinking concurrency control. So maybe you can just give us the elevator pitch for this work and maybe highlight the questions your research questions and what you were trying to answer with this work.
Yeah, okay. So I can start from the background, especially if the audience are not very familiar. I know you are very familiar with this field, but let's assume some audience probably are not very familiar with this field. So I think a CS student probably starts to get touched to a SQL database probably in undergraduate courses. Okay. So when you get into that course, you will learn that you can write a transaction which involves multiple SQL statements, okay? And if you go a little deeper into that, you know that databases can execute multiple transactions in parallel to get the best performance. Then, of course, the question is, if different concurrent transactions interleave, what is going to happen? Especially if you have learned, multi-threaded programming and locking before, you know that multiple concurrent things executing in parallel is a painful problem. Okay, but during your undergraduate course, your instructor probably will tell you that a database provides this very nice property called serializable. It basically says that if you execute multiple concurrent transactions, their behaviors will be equivalent to some serial execution of them. Okay. So in other words, you don't need to worry about concurrent transactions at all, okay? It will be equivalent to some serial execution, okay? This is called serializable. That's a very nice property. And you know that when you are writing one transaction, you're not going to worry about what other transactions are doing in the meantime. Okay, very nice property. I'm very glad to hear that. At that moment, I believe, that address all my problems, okay? And then even during my PhD, I work on topics about, how to improve the performance, how to improve various things of, executing serializable transactions. Okay, that's even to today, that's still a pretty hot research topic. But then once the multiple papers, some kind of studies, they kind of tell me that, in reality, many people are not using serializable transactions. Okay. So they are using something weaker called, the typical examples include read committed and snapshot isolation. Those are the two most common, we call it weaker isolation levels provided by popular databases. Okay, I don't want to go into the details about what's the difference between them and so on. So in short, when you are using weaker isolation levels, then you are going back to the old days that you have to worry about the interleavings. Some kind of interleavings will give you unexpected result. We probably will go through some examples. Then you need to go back to all the painful problems of risk conditions. Well, whether I need to add a locking somewhere to put something in a critical section or something not. Okay, then all the problems comes back. Then the question to me is that why? Okay, now we have this really nice world with serializable transactions. You don't need to worry about anything, but there's a lot of research on that. Okay, but why people are not using that? And if that's a fundamental reason, then maybe that has an impact on our research, right? So if people don't like serializable transactions, then maybe that's something we can address. Or if it's really not addressable, then maybe we need to research something else, right? So that's, I think, the big motivation for this problem. Okay, so basically, I want to understand that, is it really possible to let a database handle everything about concurrency? Or is it like the real world? Is it like what happens in the real world that developers still have to worry about concurrency? And then what is the separation between the database and developers? Okay, I think that's the big questions we want to answer in this work. Okay.
Fascinating stuff, yeah. Really interesting questions you're trying to answer. So, I mean, you did to sort of answer this question and explore these questions. You did a study, right? So, yes. Can you maybe tell us a little bit about the study and the way you designed the study?
Okay. So in this work, the first part of this paper is to study what really happens in real-world open source, database applications. Basically, what kind of isolation levels are people using, and if they are using weaker isolation levels, or some of them don't even use transactions, they use something called ad hoc transactions. Okay, if they're using those weaker or ad hoc transactions, are they meeting any correctness issues caused by the weak isolation level? Okay, and when they if they meet those problems, how do they fix that? Okay, and even more interestingly, so why are they reluctant to use a serializable database? Okay, so those are the questions we listed as a detailed question. So what we really do is that we go through the issue or bug reports of open source repositories. Okay, we search for issues related to comparison control in databases. Well, that's actually a painful procedure. We can go to more details if you want. Okay.
Then we can maybe talk about that later on, yeah, when we speak about some of the difficult aspects of this work. But for sure.
Yes. That's always the painful part of study work. Okay. So after we found them, we manually read them, okay, to understand what are the root causes of the problem, how people fix that problem, and if they leave any comments about, why they prefer weak isolation or ad hoc synchronization, ad hoc transactions, and so on. Okay, that's basically the methodology we use in this work.
Cool. Yeah. So, I mean, are there any limitations to this approach you took? I mean, was the alternative ways you considered when designing this, or was this sort of the obvious and best path, you think?
As I said, it's a painful process. Okay, so I would say there are two limitations of the work. Okay, so first, obviously we cannot, read everything. Okay, there are so many bug reports about open source applications, so we cannot read everything. So we try to do some search based on keywords. Okay, but it turns out that it's really hard to find the right keyword because people sometimes just call the problem risk condition, okay, so which is indistinguishable from a multi-threaded risk condition. And And multi-threaded risk condition happens much more frequently than database issue. It's really hard to find the right keyword to search. So our final strategy is that we search for issue report, which includes keywords from two fields. One field is regarding concurrency, like a risk condition, locking, concurrency, and something like that. Another field includes keywords from databases, like a database, SQL, transaction, something like that. So we finally basically only look at bug reports which includes keywords from at least one keyword from each group. Still a heuristic solution, we may miss something. So that's one limitation of our work, okay? The other limitation, and that's something we really like to do, is to see what happens in industry, like what happens in, for example, Oracle or Microsoft SQL Server, okay? We tried, but that's really a hard job because there are always privacy concerns, right? So, Oracle is, there are users using it. We cannot do a study about users' transactions that are privacy concerns, okay? That's a much painful job, okay? Even during some informal conversations with like Microsoft people, we find the quick answer is nobody knows the exact answer. Okay, nobody knows the exact answer. Okay, so that's something we really like to do. Okay, if anyone in industry has the resource or has interest to do that, we really would like to see a similar study. Okay, that's a second limitation. Or you could see the future direction.
Cool. That's interesting. If anyone's listening and has access to concurrency bug reports from their systems, please do reach out. Right? Yeah. Great stuff. It's interesting on the so these online applications that you said, like what sort of how many different databases did these applications use? Like what's the sort of and also the domains of these open source applications? Was it very wide reaching?
I would say a majority of those applications are what we call e-commerce applications, right? Online shopping, accounting or something like that. But there are a few exceptions. I remember one of them is about a gaming server, okay? And there are some about social networks or something like a wiki, okay? They use database as backends as well. But I think the majority of them are like e-commerce, okay?
Okay, cool. So let's talk about the consequences and the things you found from this study. So can you maybe first tell us about some of the data inconsistency issues you found?
Yes, data inconsistency is the most common issues we found, and that's, I would say, not surprising. Okay, so maybe let's go back to the weak isolation to see why these things happen. Then I think you can have a better understanding about what they really cause. Okay, so let's give a very simple example. Let's say you have a transaction to first read some count. Let's say how much money you have. Okay. Or let's say you want to buy something online, and your transaction will first check whether there's still sufficient count in stock. Okay. You probably will do it with a select and then do a if. Okay. And then if the amount is sufficient, usually you deduct some number from the account, and that's it, done. Okay. That's a very simplified purchase transaction online, okay? So when you execute them, let's say you have multiple people trying to buy the same thing at the same time, okay? So if you have serializable transactions, then there's no problem. Some of them will get what they want, some of them probably will not, but they will get an honest answer, okay? But let's say when you move to another very popular isolation level called read committed. Read committed will allow your select or your check to execute in parallel first, okay? So that leads to a classic phenomenon like risk condition. Basically, everyone checks at the same time. They all find there are sufficient amount of items in the stock. Okay. Then when they do the deduction, you will find probably that's not enough. Then the final count will become negative. Okay. That's a very classic risk condition problem. But now if you use read committed, it could also happen in your databases. So let's say if I'm a company like Amazon, I sell things and I use a read committed database. What could happen is that I may oversell my items. Okay, I may have 10 items in stock, but if everyone checks in parallel, I may sell to 100 customers. Okay, so let's call it overselling. Okay, or let's say if you save some money in the account, it could also cause a problem called double spending. Basically, I can try to spend my money at the same time to buy two different things, and the system will let me pass, okay, and leaving me with a negative account number. Okay, this is called double spending. Or if your system have something like coupons, vouchers, and if the customer is smart enough, they can use it more than once, okay, by issuing concurrent transactions at the same time. So this is called double spending, overselling. Those are classic problems which are caused by the data inconsistency issues, okay. Another very classic is called ID problems, okay. So most of these companies want to ensure that when you have an order, you have an order ID, okay, and the order ID should be unique so that we can track what happens with each order, okay. But again, if you use a really committed database, it is possible that two orders will get the same ID, and then everything will mess up. You may get things from another order, or your item may go to another order, okay. So it's hard to predict what could happen. So those are the, I think, most common, data inconsistency issues we have observed.
Nice. So out of, I think you say in the paper that you found like 93 bugs, I think it is, if I'm remembering correctly. So yes. of those, how many were related to data inconsistency?
78.
Okay, so that's sort of the lion's share almost of issues were around inconsistency, because you also define like another category of issues, right, that you've identified as unavailability.
They usually cause the process or the database to crash, but doesn't cause your data to be wrong. Okay, so common issues like if you have two delete transactions deleting the same row, okay, one of them will throw exception, okay. And if you don't catch that, then your process will crash, okay? And sometimes deadlock is another possible reason, okay? Those, I would say, they are not specific to weak isolation levels, okay? Even if you use a serializable database, some of those issues could happen as well. That just says, even with a serializable database, a small amount of these problems will still happen. So developers still need to be careful about some aspect of concurrency control. Okay, but some of them are related. Okay.
Cool. And so I guess the question that kind of follows from this is then, of these issues that you identified, how severe were they? How bad were they?
Okay, that's actually the most interesting question we find. Okay, so maybe still let's go back to the history a little bit. Okay, so I mean the problem with weaker isolation levels are pretty well known. People know that they could cause data inconsistency issues, right? So it's a risk condition. It could happen. Okay, so far, but many people are still willing to use that. So one question there is that, do those issues really happen? Okay, because maybe most open source users probably don't really have a very high throughput, right? So you probably get a few orders every day if you are just a startup, right? So maybe those things, risk conditions don't happen at all. So that's a guess, okay? But at least from our study, we find, at least for some people, those are not true, okay? We see that common thing. One guy said this problem happened 5 times over the past few months in a total of 10,000 orders. So if you have 10,000 orders in 5 months, that's really not a lot, right? So your system is idle most of the time, but those issues still happen. Okay, our guess is that you may have some kind of a burst of incoming orders at the same moment in a short amount of time. So the short answer to your question is that it is more severe than we expected. Okay, so at least I would expect that for a person with tens of orders every day, this should not be an issue. But it seems that it could still be an issue sometimes, okay? But if you ask me what are the real, financial costs to them, none of them provide that data, okay? So I cannot answer that directly, sorry. Since they complain to the developers, that must be an issue for them, okay?
Yeah, that's true, yeah. That's interesting that even with sort of what we'd sort of think of being a quite a low, well, not low, but like not like you can't really imagine 10,000 orders, for example, generating like the sufficient level of contention or stuff. But I mean, like I said, if the workload's quite bursty, then that kind of, I guess, could be an explanation for that. But yeah. That's a really good point. So there's kind of in your paper, you then sort of like break down the causes of these bugs into, and then it's like you categorize them into 6 different categories. So maybe we could run through these categories and you could tell us about what they are, right?
Right. Okay. So the first one is similar to the example I just described. Okay, and actually that's the most common issue among all the 93 issues. 52 of them are caused by that. So basically, that's a very common pattern. As I said, you first have a select statement to check something, and if the check passed, you do an update. Okay, so we call it read followed by write. Okay, and if you do those kind of transactions on a read committed database, you are almost guaranteed to have some issues if you have a high level of concurrency. Okay, so it can be further broken down into 2 types, but I think I will not go to details here. Okay, so if you're interested, you can always read the paper. Okay, but that's the most common pattern to cause issues, especially when using read committed. Okay, so the second category is inappropriate error handling. That's mostly related to the unavailability issues we have discussed. Okay, so if concurrent transaction could throw an exception and you don't handle that, okay, that's an issue. Okay, the third issue is lock timeout. That's usually caused by deadlocks or too many concurrent transactions. Okay, again, that's not something specific to concurrency control, but the most interesting thing we find for this problem is that sometimes people argue that to reduce the timeout or to reduce the locking time, we should use a weaker isolation level. Okay, even weaker. Okay, one comment, for example, saying the default isolation level is a repeatable read. Okay. Then the developers argue that we should move it to read committed to reduce locking times, to remove this lock timeout problem. Okay, that's pretty interesting. The other issues I think they're pretty minor, so I maybe not go through them here because they only happen to 2 or 3 lines. Okay, but the last category is a big one because there are some issues, 22 issues we have not been able to identify the exact root cause. Okay. Because some reports are still open, okay, and sometimes people fix problems in ad hoc ways. Just to say, I disable that, I change a little bit here, then problem disappear. Okay, fine, good, okay. But then you don't know the exact root cause. Okay, so yeah, some issues fall into this category, so we don't know the exact answer yet. So in short, read followed by write is still the most common pattern to cause problems.
Cool. Yeah. So those are there's a majority of that's the majority cause for mostly. So that's interesting. So like how you alluded to it a little bit there when you discussed like the other category, like the unresolved sort of issues you found. But what sort of, I guess, like how do developers go about fixing these bugs that they found? How did you observe like the approaches that they use to fix these bugs? Yes, other than just like turning something off.
Yes. That's actually, I think how to fix the issue, the answer to that from our study is the most surprising part of our study. The short answer to that question is that people don't have a unified solution to that. Okay, different people use different solutions. Many of them are very ad hoc, and some of them even contradict with each other. Okay, they follow different philosophies. So maybe again, let's start from history a little bit. Okay, so as we said, it's not a new problem. People are aware that there could be consistent issues caused by weak isolation levels. At early days, some people's argument is that it's fine. We can let them happen. Okay, then we fix them manually. If you think about the overselling issues, right? It could happen to Amazon, right? It could happen to an airline. An airline actually do that deliberately, right? So the oversell issues, okay. But then when problems really happen, what do? Amazon will send you an apology email saying, sorry, it runs out of stock. They may give you some compensation, like a voucher or something. The airline will say, okay, so if you're willing to give up your seat, we will give you a couple of $100. Okay, so those problems can be fixed manually. Okay, and it doesn't have to have a technical solution. Okay, so those are the arguments from early days. I mean, that makes sense to me. Okay, that makes sense to me. But in our study, we find the answer is very different. For the 93 issues, only one issue discussed this what we call business solution. Okay, and it's not clear whether they finally adopted it. So in the open source field, people are, at least from our study, we conclude that people are not happy with those business solutions. Okay, we don't know the exact reason yet, but our guess, or from what we look, okay, the open source community is quite different from, those closed industries. If you think about Amazon's database team and or whatever storage team and their product selling team, they are all under the same organization. They are all under Amazon. Okay, so they can coordinate their responsibility. Okay, you could say who is responsible for fix the correctness issues caused by reclassification. They can coordinate that. But in open source community, it's very different, right? So the database provider and the database application are two separate organizations, okay? If you use MySQL, right? So MySQL now belongs to Oracle, but it used to be open source, right? Postgres, right? So, and for those people who use them, they are in different organizations from the creator of the database, okay? So now the question is that, like say, if I'm a user of MySQL, okay, let's say I write a program or I use some online shopping software on it, and I find my software oversells, okay? So am I going to fix my problem in my way, or am I going to, blame MySQL or blame those who provided the, shopping software, okay? So that's why the story in open source community might be very different, but that's our guess, but that's from our observation, okay? So that's why we're particularly interested to see what happens in industry like in Microsoft and Oracle, because or in Amazon, the equation there might be very different. Okay, but let's go back to the question, how do they fix it? So the first answer is that in open source community, people are not very happy with business solution. They want a technical solution to fix the issues. Again, it's not a new problem. So the database community have, I would say, are aware of these issues, so they provide some help for that. So one specific semantic is called a select for update. Okay, basically, as we said, if you do select and update, and you do it on the read committed, then the database may execute the select in parallel. Okay, now select for update is designed to prevent this case. If you say I declare a select with additional keywords for update, then the database knows that, okay, so I'm going to do an update after the select. So I should not execute two of those selects in parallel. Okay, I should just treat the select as some kind of update. So if you imagine this, this is an exact solution designed to address the problem we have just discussed. Okay, and actually in our study, we have searched for this keyword, for update keyword specifically. So our study is a little bit biased to for update. But despite such bias, among the 93 issues, only 22 of them use this solution. Okay, so a small percentage of them use this solution. Okay, so, and if we look at all the other solutions, all of them are very diverse. Okay, so for example, some of them decide to just add a lock. Okay, saying maybe I do select, I call lock before select and call unlock after doing update. Okay. But in databases, this is not very simple because a database is distributed and your web server might also be distributed. So you cannot just use a pthread lock or Java synchronized, right? So some of them actually use an external locking service like Redis. Okay, so you need to grab a lock in the service, then you need to send a locking request to Redis before execute the transaction and release the lock afterwards. Okay, so this is called additional locking in our paper. There are some people that even do it in a more crazy way. They implement. If you are familiar with database concurrency control, you probably have heard about optimistic concurrency control called OCC. So what they do is that they don't use a lock. They add a version to each row. Okay. Then at the end of the transaction, they check whether your version matches. I don't want to go into the detail, but That's another way to do concurrency control in database. But traditionally, this is implemented by the database itself. But now we find at least 8 issues. In 8 issues, the developers implement them by themselves in the application layer. So basically, for their table, they add a column called version. Okay, and when they do the select, they read the version. And then when they do the update, they put the version in that column. And then at the end, they check the versions are matched. So basically, they re-implement OCC by themselves. Okay, so then the question is, what are we doing, right? Those are supposed to be the job of database, not supposed to be the job of developers. Okay, and there are many other answers. For example, some of them saying, okay, no, let's give up concurrency. Okay, I just execute those transactions in serial order. Okay, so for conflicting transactions, I just execute them in serial order. Okay, the one thing particular is that actually one original question we want to ask is that why are people not willing to use the serializable? Okay, we find that only one of the cases decided to use serializable ultimately. Okay, so they said, okay, let's upgrade to serializable. Okay, 6 other issues decided to upgrade isolation level to some extent, but altogether, only 7 issues. In 7 issues, people decide that okay, using a stronger isolation level is the solution. In all the other cases, they move to other solutions. So in short, the solutions or the fixes are very ad hoc and very diversified, and some of them are very complicated. Okay, so that's why we raised our original question. So do we really, is database really able to handle everything by itself, or do we want to push the responsibility to the developer? And if we really want to do the push, then can we make their job easier? Okay, instead of re-implementing OCC just at the application level. Yeah, there are a few other categories. So if you are interested, still encourage you to read the paper. Okay.
Sure. I find that absolutely wild that, well, there's 2 things that jumped out there. First of all, like the people basically re-implement OCC is crazy. It feels like such a wild solution to the problem. And then that they use an additional like lock-in servers as well. Like it's crazy that some people like reach for that like that sort of solution that a database should provide for you, in my opinion, anyway.
Right.
So it's really interesting to see that, and it kind of the additional lock-in feels like massive overkill almost. But anyway, that's really interesting. That's the kind of solutions that people reach for with these sort of problems. That's cool. So you touched on it a little bit there about like how these findings helped answer your question you asked prior to the study. So maybe you could elaborate on that a little bit and sort of like look back on the questions you asked and how now that you can answer them, now you had this new knowledge.
Okay. So here I just list a few questions people have asked in the past. So we're not the first one. So first question we have discussed. Okay, so do weekly isolation levels really cause any issues? Okay, because people's guess is that maybe you don't have a high contention level, so maybe that's fine. So our quick answer is yes, they still cause issues. Our guess is that maybe there's a burst of traffic to some extent. Okay, despite that, the application does not seem to have a sustained high throughput. Okay. So the second question is how much effort does it require to handle those correctness issues caused by weak isolation? Our quick answer is it's a lot. Okay, so our general finding is that it's not hard to diagnose or reproduce the problem. So this is quite different from traditional bug detection. Usually it's it's hard to diagnose the bug, but after you know the reason, it's easy to fix that. Okay. But here it's the opposite. Okay, it's pretty easy to diagnose or even reproduce them, because as we said, the pattern is pretty straightforward. Most of the issues are caused by read followed by a write. Okay, but fixing them is a lot of harder. Okay, that's why again we raise our question. So the problem there is that databases may still work under the assumption that we handle everything about concurrency control. But in reality, it is not. But when it is not, it also doesn't provide additional support for the developers to customize the concurrency control. That's why they have to rely on additional locking, implement OCC by themselves. So to me, it seems that this gap, basically, database wants to do everything, but actually does not do everything. basically this gap makes concurrency control even harder than just give everything to the developer. Let's say I don't do anything, just you do locking for everything. Okay, now things become even harder than that to some extent. That's why, okay, so the short answer to how much effort does it require is that it requires a lot of effort to fix issues. Okay, because some of them even need to rely on external systems, and some of them even need to rely on multiple external services. Okay. So the last question, actually, that's the most interesting question we are interested in, is why people are not using serializable. Why are they not even using select for update? Right. So select for update, if you think about it, it's somewhat similar to the idea of serializable. Basically, you hold a lock for longer time, right? So for sure. So I think in the past, people believe, or at least my feeling is that serializable database are not going to provide enough throughput compared to weak isolation levels. Okay, which is true, but the problem for the open source community is that, as we said, most of them don't require a sustained high throughput. Okay, so throughput probably is not the major concern here. Okay, so we carefully go through discussions to see if people discussing those things. Most of the people don't discuss those, but from a few discussions, we find there's a general concern about the locking. So basically, if you use a serializable database, the database will hold the lock, especially hold the write lock, for longer time compared to really committed snapshot isolation or even using no transactions. So this leads to a longer locking time. This also leads to a higher chance of deadlocks. Okay, now in today's database, I think to detect the deadlocks, most of them use a simple strategy, like you set a timeout. Okay, saying if the transaction does not return in a minute, okay, let's kill it and retry. Okay. In one discussion, we find that people are really struggling to set the right timeout interval for deadlock detection. Okay, so if you set it too short, then a heavy transaction will always be killed. Right? If you set it to be 1 second, right? If a transaction takes 10 seconds, then it will always get killed. If you set it to be long, like an hour, then it will slow down your recovery, right? So if a transaction really gets into a deadlock, then you will have to wait for 1 hour for it to finish. Okay, so I'm quoting some of the comments here. Let's see. Okay. That's a quote from one developer, which I totally agree. So it is a poor approach to architect software based on guessing deadlock timeouts. Okay. So actually, personally, during my research, I've met the same problem in many other fields. Okay. I've seen many other problems. So basically, our answer to why serializable or why not select for update is that they may introduce longer locking. They may introduce a higher chance of deadlocks. And if we just use timeout to detect deadlocks, and people find it's a pain to set up the right timeout interval. And as a result, some of them are even willing to go to all those complicated and ad hoc solutions. Okay, but again, this is just from limited, probably 4 or 5 comments. Okay, so those, if you have any answers, if the audience have any answers, we are very happy for further discussion.
Cool, great stuff. It's mad that just because of being it's difficult to determine what the optimal lock timeout should be, that it drives people to use these sort of what seem to be sort of extreme solutions almost. It's really interesting to see that's what people do. So I guess kind of building off of this, what can we do then? So what can we do as researchers, and also what can software developers do to make this problem better, right? So to alleviate the problems associated with concurrency bugs.
Okay, so that's a question we discussed in the paper, but honestly, we don't know the absolute right answer. Okay, so that's why we are writing this. Side of paper is usually motivate more discussions. Okay, yeah. So but those are here. I'm listing our opinions. Okay, so in the short term, let's say if you don't want to do anything crazy that needs 3 to 5 years, I think first between the 2 most popular isolation levels, snapshot isolation and reader committed, I think snapshot isolation provide much better correctness guarantees, which again is probably not surprising. Okay, people know it's stronger. Okay, so actually snapshot isolation will remove, I think, a majority of the issues during our study. Okay, and another major help is from those databases which provide some kind of, they call it unique IDs. Basically, you can declare one row as unique, and the database will help you to generate some unique IDs or incremental IDs. Okay, so this feature will remove most of the same ID problem we have discussed. So I think by combining snapshot isolation and this unique IDs features from databases, we can address most of the issues. Okay, so during our study. Okay, but whether snapshot isolation database will cause more issues, okay, we don't know yet. Okay, but at least that's the result from our study. Okay, from the research side, so we discuss in two directions. So first, could we push all the responsibility to the database? Is it possible to improve the database design so that it can be serializable? It doesn't have any of the issues reported by different developers. Okay, as I said, we don't know the exact answer. We discussed a few possible ways to improve it, but at least if you ask my personal feeling is that it's not going to be able to handle everything. Okay, because there are always knowledge that only a human being knows. Okay, for example, typical example is that, okay, some developer may say, okay, one of my transactions doesn't need a serializable result. Okay, it says, I read some statistics. I'm fine with some errors. Okay, those kind of things are really hard to be figured out by the database by itself, right? So, so my opinion is that some kind of developers help is going to be useful. Okay, although AI is popular today, we cannot expect what AI can do maybe in 10 years. Maybe if you have a very smart AI, then maybe we can do the job fully by the machine. But so far, that's my opinion. So then the last question is, if we need users' help, okay, so how can we do that? We don't want a user to implement OCC by himself, right? So that sounds like ridiculous. So is there a better way so that the database can expose something to the developer? And for example, if you use locking, it may expose locking to the developer to some extent. I know some databases can already do that. Okay, if we are using a versioning database, can we provide the versioning versions to the user so that it can do some control by himself? Okay, so that's the last question we have discussed. Again, we don't have the concrete answer, but I personally think that's a direction to explore.
Nice, plenty of interesting directions for us to explore. Then that really I guess sets the scene for your future research, right? So maybe we can touch on, I guess, where do you go next, and what's next on your research agenda with this work?
So I think we are going into both directions. So we are seeing whether we can develop any automatic analysis method to help people, figure out what could go wrong if you're using a weak isolation level, and maybe automatically fix some of them. Okay, and also we are thinking about, how to. So what is the right abstraction between the database, concurrency control, and the user? Should we expose anything? What to expose? But the challenging part is that if you expose something, maybe it will break other things, right? Your database also have this nice, rollback support, atomicity support. If you expose, locking to users, those properties may easily be broken. Okay, so right. So how to expose something with a new abstraction without breaking existing things? I think that's a challenging question. We're thinking of. Okay.
Nice, cool. So I get that. Yeah, really interesting direction. That'd be really nice to see kind of your future work on that. I guess I think you alluded to this a little bit earlier on in the chat as well, but I would love to kind of get your thoughts on what was maybe the most unexpected thing that you sort of encountered while working on this.
Yeah, the most unexpected things is that I have been working on a serializable database from an undergraduate until the end of my PhD, but then when I realized that most people are not using it, so that's the most unexpected.
That's wild. Yeah, you think, what the heck have I been doing for all these years, right? Yeah, that's cool. I'd like to get a little bit more about the origin story about this paper as well. And so, I mean, from your initial sort of conception of the idea, I guess first of all, can we say, how did this idea come about? And then also tell me a little bit more about the journey from sort of the idea to now and to the side of publication.
Right, that just goes back to my answer, right? So I have been, even my colleagues, we collaborate on, serializable databases for a while, okay? But then we see those studies. After we see the study, we look at the real applications by ourselves, right? We look at the source code, yeah. Many of them are not using serializable databases, okay? So why? Okay, so if there's a reason we can address, that could be a nice research, okay? If there's some fundamental reason we cannot address, then it could motivate the research in the other direction, right? So, yeah, that motivates this work and potentially all the future works follow up. Okay.
Amazing. That's really cool. I mean, whilst we've got you here, could you tell us maybe a little bit more about your other research? I mean, I don't know whether you're able to elaborate on what you're working on, obviously at Meta at the moment, but maybe in your wider sort of research, what are you looking into at the moment?
So, as I said, I'm a sabbatical at Meta. Okay, so here, instead of doing real research, I think I'm in the learning phase now. I'm trying to learn, what industry really cares about. Okay, so in the last half a year, I mainly work on software deployment. Basically, they have a new version. Let's say they have new versions almost every day. Okay, so their old version is already deployed to millions of machines. How do you deploy the new version? Especially you don't want to stop all your service and then do upgrade, right? So that's a topic I worked on last year. This year I'm working on something related to scheduling AI training jobs. Okay. Which is a pretty hot and new topic listed. Well, I wouldn't say it's new, but it's a hot topic this year. Okay. In my universities, as I said, we still have some follow-up works for transaction processing. And in the meantime, I'm also interested to see how to apply some of the new AI techniques to help the design of the system.
Amazing stuff. Do you find that sort of having the experience of being in industry to versus being in sort of an academic sort of environment, that the things that academics think are important differ or diverge from what industry thinks is important in terms of what needs research? Do you feel like they're quite aligned?
Oh, that's a very big question. So first, there's a big difference for sure. Okay, that's a big difference. So they're different in many different ways. Okay, so first you could say research is usually ahead of industry by maybe 10 years. So basically, you would say many problems have been discussed in research papers several years ago, but they have not been applied in industry. It's not because they are not good ideas. I mean, I talk to some people. People think they are good ideas, but they just don't have the time to do that yet or explore that yet. Okay, so research is ahead of that. So so that's one difference. The other difference is that there are many more constraints in industry. Okay, so whether your research can be applied. For example, like in our research, we sometimes to do program language analysis, right? So we analyze your code to see whether there's a bug or whatever. Okay, in Meta, for example, okay, so not everyone is using the same program language. You use Python, Java, PHP, whatever. You could have like 10 very different languages. Okay, so if you want to do program language analysis, then we need to implement it for 10 very different languages. Okay. That's a job, that's very hard.
Yeah, it's like a nightmare.
So there are a lot of additional constraints there. Also, industry is much more careful about overhead, right? If you write a research prototype, say 5% overhead, that's pretty good. Okay, no here. If it's over 5, it will be rejected directly. Okay, so there are many differences. I think, probably don't have time to go through all of them today, but those are the major things in my mind. Okay,
that's really cool. I mean, I guess sort of along the sort of similar sort of line is, I mean, how do you approach sort of determining what is worth working on and like sort of generating ideas, I guess, right? Like, how do you determine this is the thing that needs working on? Like, what's your process for that?
Okay, so first, to be honest, I was often wrong. Okay, so so there are multiple topics I pursued in the past, which turns out to be not so good. Okay. I don't think there's a unified answer to that. Okay, so what we learn is that we usually learn by reading other people's publications, okay, and discussing with other people, both in industry and academia, so that we can see what are the important problems. Okay, then we will choose based on my interest. Okay, so of course I cannot work on everything, so I will choose those topics based on my interest and expertise. I think that's how I usually work on find topics or whatever. Okay, but again, as I said, I'm often wrong. So
no, that's cool. That's a great answer. That's a great answer. I guess yes. Like we've mentioned this at various points through the interview, but I mean, what do you think is the biggest maybe challenge in database research right now, or in distributed systems even maybe, or just sort of in our sort of field in general?
Oh, okay. Yeah, that's a question probably too big for me to answer, but I will try my best. Okay.
Yeah, speculate. Yeah.
Okay, so regarding what problems I think are interesting or important for database, so one thing I find is new applications, in short. Okay, so again, if we go back to the history a little bit, okay, so in the old days, there's only databases. Everyone's using database. Okay, then starting maybe from Amazon Dynamo, there's a trend called NoSQL. Basically, it says you have a very simple application like a key value store. Okay, so then let's just build a key value store with a key value store interface. We don't need a full transactional database for that. It gives you better performance, but of course you lose other things. There's some controversial about which way to go. But I think in this few days we have seen many more applications like we're familiar with like a graph database, analytics database, okay, and time series database, and also array database. Okay, I have worked on some of them. So I think the big question here is that, do we still want to put everything under the hood of database, okay, and analyze everything with some kind of a SQL transactions? Or do we want to build some specialized systems for them? Okay, so a specialized system usually gives you better performance, lower cost. But, still, many people still prefer to store everything in database because it's mature, it gives you an easy query interface, and everyone is familiar with SQL, okay? I don't know the answer. I see research in both fields, so I think the question I'm interested in is to say which way is the right way to go. So should we still put everything on the SQL database, or should we build a specific system for each application? Okay, that's one question I found interesting. The other one, which I'm not very familiar with, but I see a lot of work on that, is how can database handle this, what we call disaggregated mode, okay? So in the old days, your CPUs, your memories, your storage are on one machine, so everything's close to each other. But now in industry, there's a trend saying, let's say you put all your memory on the remote machines, okay, and you also put your storage on another set of remote machines. This gives you a lot of flexibility for resource provision. Of course, you have a longer latency, okay? So can you design your database efficiently on such a mode, okay? So that's another question I found interesting, although personally I haven't worked on this field yet. Okay.
Cool. Yeah, we should check back in like 5 years, right, and see if these see if these predictions are like questions have sort of come to fruition. That's cool. Great stuff. So it's time for the last word now. So, what's the one thing you want the listener to take away from this podcast today and from your research?
I would say if you're a database user and you have not heard about weak isolation levels, you should definitely try. Okay.
Okay. Cool.
Yeah. I actually did some informal survey in the department. Okay. Yeah. So just in the class, okay, ask a student how many people have heard about isolation level. Most of the answer is no. And imagine those are the people that are going to go to industry and use databases. That's a pretty risky scenario in my opinion. So I'm trying to incorporate those contents in the courses, but so far it's only done at the graduate course level, graduate operating system course, and database course level. but yeah, I just think it's a problem. It's a problem since, weak isolation networks are so popular, but most people who are using that are probably not even aware of that. Okay. Yeah. That's a warning sign, in my opinion.
Yeah, agreed. Especially, I guess, as a lot of the most popular systems ship with the default isolation level set to a weak one, right? Most systems ship with read committed, yes. Right? I think. Yeah. Yes. So, yeah, no, it's a really good point, and hopefully the listeners take a note, and now more people know about weak isolation. So, fantastic, Yang. Well, thank you very much for coming on the show. It was a great conversation, and we'll drop links to all the relevant materials we've discussed throughout the episode in the show notes, so the listener can go and check those out. And yeah, thanks very much, and we'll see you all again for some more awesome computer science research.